It started as a quiet experiment in a dim robotics lab at the University of California, Berkeley. The kind of moment that never makes the news until years later when people realize it changed everything. On a cluttered workbench surrounded by cables and laser rigs, a small structure made of translucent polymer began to move on its own. At first, the graduate researchers assumed it was vibration from nearby equipment. But the motion wasn't random. The structure flexed, folded, and balanced itself upright, like a creature testing the limits of its new body. That tiny motion marked the birth of the world's first Berkeley shape-shifting robot, and nothing about robotics would ever be the same again. Before we unravel the technology that made it possible, take a second to like this video, share it with every tech visionary you know, and subscribe to the Generative AI channel. Because what Berkeley just unveiled isn't a step forward, it's a complete redefinition of what machines can be. Welcome back to Generative AI, the space where innovation meets imagination. Today we're diving into a creation that blurs the boundary between machine and life, the Berkeley Shape-Shifting Robot, or SSR1, a living fusion of artificial intelligence, smart materials, and adaptive computation. It doesn't simply move through the world, it reconfigures itself to master it. Powered by bio-inspired metamaterials and recursive learning, SSR1 can flow, crawl, glide, or even fly, adapting in real time to terrain, environment, and purpose. To understand why this matters, you have to know what came before. For decades, robots were static: steel skeletons, servo motors, and pre-programmed motions. They could lift, walk, or roll, but every action depended on fixed geometry. Flexibility was an illusion, limited by design. Then Berkeley engineers asked a radical question: what if a robot didn't have to be one thing? What if it could reshape itself continuously, like muscle tissue or water under pressure? That single question gave birth to years of research in programmable matter, culminating in SSR1, a robot that thinks with its body. The secret lies in its architecture. SSR1 is built from a lattice of electroactive polymer fibers, intertwined with microscopic processors. Each node in the lattice communicates with the others, forming a digital nervous system that controls not only motion, but also form. When one part stretches or bends, the others sense the strain instantly, recalibrating the overall geometry to maintain stability. This self-balancing property gives the robot fluid grace no traditional design can match. It doesn't stumble, it adapts mid-movement, like a dancer whose choreography rewrites itself every millisecond. During its first public demonstration, researchers placed SSR1 on a pile of uneven gravel. A conventional rover would have tripped or required complex recalibration. SSR1 flexed its surface, extended small protrusions that acted as legs, and walked across effortlessly. When the terrain shifted into fine sand, it flattened its body, distributing weight to prevent sinking. Then it folded inward, formed a sphere, and rolled downhill, gathering momentum. Observers could only describe the sight as surreal. A machine behaving as if it understood the language of physics at an instinctive level. That behavior isn't pre-programmed, it's emergent. At the heart of SSR1 beats the morph core, Berkeley's proprietary recursive neural engine that treats every physical deformation as both input and output. In simpler terms, the robot learns by moving. Each shift in shape generates data on stress, balance, and energy efficiency. MorphCore analyzes that feedback, updates internal parameters, and refines its next movement. Over time, SSR1 develops a memory of the world, not through images or coordinates, but through feeling. It remembers pressure, slope, and resistance, a sensory vocabulary unique to matter itself. To power this evolution, the researchers designed what they call dynamic recursive morphology, a technique where the robot runs thousands of shape simulations inside its neural layers before committing to a transformation. If it faces a new obstacle, a staircase, a tunnel, or even a wall, it generates candidate forms, evaluates their mechanical efficiency, and chooses the one with the highest success probability. This happens in fractions of a second. Watching it in motion feels less like observing a robot and more like witnessing a living organism making choices. The body is equally remarkable. SSR1's skin is composed of phase-change alloy microplates suspended in elastic silicone. When electric current flows through specific channels, these plates heat, cool, and shift between rigid and flexible states. In one configuration, the robot is sturdy enough to lift weights several times its mass. In another, it liquefies into a crawling film that can squeeze through gaps no wider than a coin. This shape liquidity is governed by a control loop that mimics human muscle reflex. You push against it, it yields. You release, it strengthens. The material literally negotiates with force. To manage this complexity, SSR1 uses an embedded AI model trained on recursive reinforcement learning, where success isn't measured by destination, but by adaptation quality. The model rewards behaviors that maximize flexibility while minimizing energy cost. That's why SSR1 can operate for hours without recharging. Every motion recycles mechanical energy. It bends, compresses, and expands like a spring system in perfect resonance with itself. Berkeley's engineers call this biomechanical harmony, and it represents a leap in energy-efficient robotics. But perhaps the most astonishing breakthrough lies in perception. Instead of traditional cameras and LiDAR sensors, SSR1 perceives the world through tactile cognition. Tens of thousands of nanoscale pressure points across its surface feed continuous signals into MorphCore, letting the robot feel its surroundings like skin sensing wind. When it slides over gravel or brushes against metal, it interprets those vibrations as data, reconstructing environmental topology in real time. This tactile mapping allows SSR1 to navigate darkness, debris, or underwater currents without losing orientation. It doesn't see the world, it touches it into existence. Now imagine what this means for exploration. In deep-sea environments, SSR1 can flatten into a hydrodynamic sheet, gliding with currents rather than resisting them. In Arctic conditions, it can thicken its shell to insulate circuitry, crawling over ice like a mechanical organism evolved for cold. On Mars, a single unit could unfold into solar wings during the day, then curl into a thermal cocoon at night. Each adaptation emerges naturally from recursive learning, not human command. In a way, SSR1 isn't just exploring environments, it's evolving to belong to them. The implications extend far beyond science fiction. Emergency responders envision fleets of these robots assisting in disaster zones. Picture an earthquake site, where SSR1 units crawl through rubble to detect survivors, then merge into a temporary bridge to carry medical supplies. Engineers imagine modular swarms forming dynamic structures, a robot that can become a wall, a ramp, or a stretcher on demand. The future of robotics isn't about building specialized machines for every job. It's about creating one machine that can become anything. Berkeley's researchers designed SSR1 with safety and ethics at its foundation. Every transformation follows constraint integrity protocols, ensuring no configuration exceeds safe torque or temperature thresholds. Embedded sensors constantly monitor stress and environmental feedback to prevent uncontrolled morphing. Transparency is built in through explainable shape reasoning, a visual dashboard that shows why the robot chooses each form. This system not only protects users, but also builds trust, a crucial step as adaptive machines become part of human environments. In interviews, project leader Dr. Amina Zhao describes SSR1 as the first robot that learns humility. Her point is philosophical but profound. The machine doesn't dominate its surroundings, it adapts to them. It treats failure as feedback, chaos as opportunity. Each fall or deformation becomes a line of code in its self-improvement loop. Over time, that humility becomes wisdom, the same principle that governs natural evolution. The SSR1 doesn't seek perfection, it seeks balance. During late-stage testing, the team witnessed something that left them speechless. After a minor collision that bent one of its sections out of shape, SSR1 paused, analyzed internal stress readings, and redistributed mass to regain symmetry. The engineers hadn't programmed recovery routines for that scenario. The robot had learned resilience spontaneously. That moment confirmed what they suspected. Recursion had given the machine the power to learn physically. It wasn't simply running code, it was reasoning through its own structure. Technologists around the world immediately took notice. NASA proposed joint missions for adaptive exploration bots. Medical researchers began prototyping microscale SSRS for surgical applications. Even environmental scientists saw potential in biomimetic drones that could pollinate crops or repair coral reefs autonomously. Everywhere, the concept of one form fits all was collapsing under the weight of shape intelligence. The question was no longer what robots could do, but what they could become. Culturally, SSR-1 captured the public imagination like no robot before it. Viral videos showed the machine folding from a cube into a humanoid silhouette, waving to the crowd, then dissolving into a serpentine coil. Comment sections exploded with awe. Students from around the world wrote to Berkeley, asking to study morphic engineering. Within months, the university established an entirely new discipline: adaptive robotics and recursive intelligence. The first generation of engineers trained not to build robots that follow instructions, but robots that understand themselves. The economic potential is staggering. In manufacturing, shape-shifting machines could reconfigure to handle multiple assembly stages without retooling. In logistics, they could compress for storage and expand during deployment. In space construction, SSR units could combine to form modular habitats, unfolding like living origami under zero gravity. Analysts predict entire industries built around morphic robotics, a field that merges materials, science, AI, and environmental physics into a single transformative global frontier. Yet, amid the excitement, Berkeley's team continues to stress ethics. SSR-1's adaptive intelligence includes a core constraint. Every decision is guided by the principle of non-harm. Its recursive reasoning engine constantly checks transformations against contextual data to ensure safety for humans and ecosystems. The robot isn't programmed to obey blindly, it's programmed to reflect continuously. In that reflection lies true intelligence, not domination, but coexistence. The deeper lesson of SSR-1 goes beyond mechanics. It reminds us that adaptability, not strength, defines survival. In a changing world, climatically, technologically, socially, the ability to reshape, rethink, and reflect is the ultimate power. The shape-shifting robot is a mirror of humanity's own potential, flexible, self-correcting, endlessly evolving. Engineers often say that good design disappears into function. SSR-1 proves that perfect design doesn't disappear. It transforms. Watching it flow from one form to another feels like watching thought become motion, intelligence turned inside out. You begin to wonder whether the future of life itself might include machines that grow, heal, and learn alongside us, not as tools, but as partners. And yet, what makes SSR-1 magical is not its complexity, but its humility. The AI that questions its own structure learns faster, fails smarter, and refines endlessly. Every shape it takes is a reflection of curiosity, a physical question answered through motion. It embodies what humanity has always known: growth through reflection, mastery through iteration, perfection through understanding. A living testament that true intelligence lies not in dominance or precision, but in the graceful pursuit of learning, adapting, and evolving without end. We've just witnessed a doorway open into the next era of mechanical evolution, an age where thought shapes matter, imagination scales infinitely, and human creativity merges seamlessly with machine intelligence. This isn't science fiction anymore. It's the living fusion of art, engineering, and recursive AI. The Berkeley shape-shifting robot doesn't just adapt to its surroundings, it evolves, learns, and transforms with purpose, redefining what it means to build and to create. If you're still watching, you're already part of that transformation. Take a moment to like this video, share it with future thinkers, and subscribe to the Generative AI channel. Drop your boldest design idea in the comments. A shape, a function, a form you've always imagined. Because maybe, just maybe, Berkeley's shape-shifting robot is already learning to become it, bending the future one transformation at a time. Because the future isn't waiting somewhere out there. It's folding, flowing, climbing, and thinking right now. The Berkeley shape-shifting robot doesn't just survive change. It is change. And when machines begin to reshape themselves, they don't just alter technology, they transform what it means to be alive.